Welcome to Lecture 4, which is Hurricane Forecasting Tips Part 3. Let's just get right into it. Okay, so I see this a lot. To say El Nino and La Nina is the cause is just broad brushing the argument, and the proof is in 2005. Also in 2004 and 1969, which were weak El Nino seasons, as the tripole was able to focus enough upward motion into the Atlantic Basin through the MDR to cause a lot more development. And also, we did have a warm Gulf in Southeast U.S., which we'll get to later on into the next lecture, which will be pretty interesting. So the biggest thing with this is no two El Ninos are the same, no two La Ninas are the same. You can have two El Ninos that produce two completely different weather patterns. And even though El Nino can typically be a detriment to hurricane season, it's not the only factor. And people broad brush this. They go, oh, El Nino means weak season. Well, that's not always the case. Again, weak in '04 and 1969, and it was around neutral in 2005, a little bit warmer than neutral in 2005. But especially with '04 and '69, with the weak El Nino, and I remember in '04 especially, because obviously I wasn't here in '69, but in '04, a lot of people were downplaying the hurricane season because we had a weak El Nino. And did we have a weak hurricane season? No. What did we have? We had Charlie and Francis and Gene and Ivan. So you got to be really careful about that. It's a piece of the puzzle. It's an important piece, but this is a large puzzle. All right, so always keep that in mind. When you have a cold PDO, and we'll explain that later, as you cool everything all around, what do you think will happen to the tropics? All right. So the PDO, Pacific Decadal Oscillation, this has to do with the ocean temperatures in the Pacific. Tropical cyclones are nature's way of taking heat out of the tropics and getting it back into the temperate regions or mid-latitudes. That imbalance is fixed by hurricanes taking the heat out of the tropical areas and redistributing it. All right, so a natural process. The heat is focused in the Atlantic, so you get more hurricanes. All right, so it's not just the La Nina. It has to do with where you bundle the heat and warmth and how to get rid of it. So this, again, a natural process. If the globe is cooling, and especially in the Pacific, because we're dealing with the Atlantic here, we're focusing on the Pacific, to correct the imbalances through tropical cyclones. So if the Pacific is cold, and we'll talk about this, you get 2/3 of tropical cyclone activity in the Pacific, and you usually get a lot of this energy taken out of the tropics, and now all of a sudden you have this huge basin that's cold. Where do you think this imbalance is going to be made up? In the Atlantic basin, okay? So this will lead into the PDO, and then we'll go into this in more depth. So what is it? This is from NOAA directly. It's in parallel with ENSO, or the SOI, or El Nino or La Nina. The extreme phases of PDO have been classified as either warm or cold, as defined by ocean temperature anomalies in the northeast and tropical Pacific. The PDO was actually fairly recently discovered, all right, by a guy named Stephen Hare, who noticed it while studying salmon migration and production. All right, so he's looking at salmon migration and production. He started looking at the ocean temperatures in the Pacific and how it affects the salmon, and then from there it kind of led into, wait a minute, we can use this for a lot more than just salmon production. We can use this for climate and long-term trends, and trying to forecast seasonal forecasts and things like that. The water affects weather big time. All right, if you live near a body of water, you know how much or how important it really is. The water's cold, it's going to make things colder for you. If it's warm, it's going to make things warmer for you. All right, so let's look at the PDO. It's from 1900 to 2013 here. Usually go in about a 20 to 40 year period. I say about 30 years. All right, so this is a decadal oscillation. Okay, this isn't like El Nino or La Nina, the 6 to 18 months. This is in long-term periods, right? You can see that. You see that long period of warmth. You see the long period of cold, another long period of warmth. And then it gets a little tricky in recent times. You're starting to see a little bit more fluctuation. It looked to me, or a lot of people thought in the late 90s, around 99, that we were actually going to enter into the cold PDO. But really, you had another warm upswing. And it looks to me like really we entered it more like '07 to maybe 2013. And even that's a little questionable, which I'll show you. Just a little more detailed. Now, when you're in a cold phase, it doesn't mean you can't have years with warm PDO, all right? So if you're in the cold PDO, it doesn't mean you can't have a year where it's warm, all right? Or if you're in the warm PDO, doesn't mean you can't have a year or two where it's cold, okay? It's just the overall average in these 20 to 40 and really, in my opinion, 30-year or so cycles, okay? So you can see that. And you can see that drop. You can see why people thought we're going into cold PDO, but look at that recent spike back up. So it's a little tricky in recent time here. And in fairness, this is fairly new discovery when you think about weather. We're talking the last 20 years or so. So it's going to probably take some time to really fine tune this. So recently, the warm and cold phases have bounced around more. In 1999, we entered a cold phase for about 4 years, and then a warm phase for about 4 years. In 2007, we entered another cold phase that lasted through 2013. And to me, that's when it was like, all right, this is the beginning of the cold PDO. But in the last 4 years, 5 years or so, it's shipped back warm. So how will this continue to evolve? Are we in a cold PDO now? I think we probably are, but in fairness, if it stays warm the next 3, 4, 5 more years, maybe we aren't. Maybe we haven't quite gotten into it yet. I think we are, but it'll be interesting to see how this evolves, all right? So when you talk about the warm phase, you're talking about a horseshoe of warm water surrounded by a pocket of cold. When you talk about the cold phase, the opposite, pocket of warm surrounded by cold. And when you look at this, what does this kind of look like? That looks like El Nino. That looks like La Nina, right? Well, it makes sense. Cold PDO, it's going to probably influence La Ninas, and a warm PDO, it's going to influence El Ninos, okay? Now, again, if you have a cold PDO, it doesn't mean you don't get El Ninos. It's just when you get them, they're usually weaker and they don't last as long. But if you're in a cold PDO and you get a La Nina, they usually last longer and they're usually stronger, okay? That's how it influences it. So during a warm PDO, just showing you this again, you get that horseshoe of warmth and it has that El Nino look to it. And then with the cold PDO, you got that horseshoe of cold, and that has much more of a La Nina look to it. All right, so it's interesting how they tie into each other. All right, again, the PDO is a 30-year cycle, about approximately, sometimes 20, sometimes 40, but about 30-year cycle. Well, where El Nino and La Nina is more 16, 18 months. But again, cold PDO, it's going to enhance the La Nina. Warm PDO, it's going to enhance El Nino. All right. And on the flip, flipping it around. If you had a warm PDO, if you had a La Nina, it's probably going to be weaker. It's not going to last as long. If you had a cold PDO and you had an El Nino, it's probably going to be weaker and not going to last as long. Okay, so it influences each other. All right, and these tips tie into the ACE index, which we'll talk about with hurricane development in the Atlantic Basin. Okay, so let's look at this here. You got that. This is 2010. You got that clear cold PDO look. You see that horseshoe there. Now, it's not always going to look this perfect, all right? But this has a pretty nice signature there. And as we progress into 2010 and continue to the end of 2010, you could really see that cold PDO really developed with a really strong La Nina going at the same time, okay? So those were really working hand in hand. As we continue to 2011, it starts to moderate a little bit, but still cold PDO. La Nina is starting to die off, but you can see that cold PDO signature. All right, 2015. Now we don't have the cold PDO look. We have a what? A warm PDO look. Again, not perfect, but you can see that horseshoe of warmth, right? And then what do we have here? An El Nino, right? So you see how they're kind of working in tandem. 2015, really getting going with the El Ninos as we go later on. Not perfect, but you can kind of see that ring around. And then as we go later in the year, starting to lose that a little bit. It's kind of more neutral, but El Nino is still going. All right, and then as we move into 2016, you still have it. Obviously, El Nino is weakened. You still have that horseshoe around it. But, it's still prevalent. You can still see it at that point. This leads into the Atlantic multi-decadal oscillation, all right? So same thing, about a 30-year index or a 30-year trend, all right? And it goes in the periods of warm and cold, just like the PDO. But there's a lag. There's a little lag there, and it kind of makes sense. And, again, we'll talk about this in more detail. So what is it? From NOAA, the AMO is an ongoing series of long-duration changes in the sea surface temperature of the North Atlantic Basin. With cold and warm phases, it may last 20 to 40 years at the time. and a difference of about 1 degree between extremes. All right, 1 degree Fahrenheit doesn't sound like a lot, but it does make, remember we talked about buoyancy in the Caribbean and with the tropics, it does make a difference. These changes are natural and have been occurring for at least the last 1,000 years. Again, straight from Noah. All right, so these averages, and you can see where they're measured in the Atlantic Basin. Later, we're going to get into the tropical North Atlantic, which is measured slightly differently. But this one, you can see clearly that we entered the warm phase in about 1995, and there's really no doubt on that. What's interesting is what started happening in 1995 when we started entering the warm phase in AMO. What started happening? Hurricane activity started doing what? Started going up, right? Well, it makes sense. If obviously it's just one factor and it's just one piece of the puzzle, but if the Atlantic Basin starts to warm up, that's going to help hurricane activity, all right, especially from a numbers standpoint. And you can see that trend, about 95, it's pretty clear that we've been in warmth, and we're still in that warm period right now. And if you look at when they switch, there's about a 15 to 20 year lag, all right? So let's look at when we switch to the warm PDO. I would say, 77, 78 around there, and it continued at least to, I would say, about 2007. Now, there's some question here, but I think right around this range, we're starting to now go into the cold PDO. It definitely kind of looks that way to me. But you see this, 40-year block here that started in 1977. But look at that lag. Were we warm in the AMO in 1977? No, we were cold, all right? It wasn't until about 95, about, 18 years later, almost 20 years later, that it switched warm. So what happens, all right? So if the Pacific is cold, then that imbalance is going to be made up where? In the Atlantic Basin. The Pacific's warm and we're having tons and tons of tropical cyclone activity, then you're probably not going to get as much activity in the Atlantic Basin because you don't have an imbalance, okay? So again, just remember there's a lag between these, and the oceans affect the temperatures, okay? So if the Pacific is cold, then it's going to affect everything around it. It's such a large body of water, and you're going to have a net energy deficit. And if you have that deficit, it has to be made up somewhere, all right? The whole purpose of the tropics is taking energy out of it, okay? Or with the whole purpose with hurricanes and typhoons and things like that. All right, so you can see these periods, AMO cold for about 30 years, and then another 30-year period, and then warm. You can read all these. I'm not going to read every single one. But where it does get interesting is, have we entered the warm phase of the PDO? The cold phase. The warm went to at least 98. I personally think the warm went more to like 2007 or so. I do think we have entered the cold phase, but a lot of the literature was saying 99, and I think it's at least more 2007 that when we entered the cold PDO. So looking at the AMO here, you can see 2010 warm AMO. You can see all that warm water. Still in 2015 warm AMO. 2018, no, much more of a cold look to the AMO. So makes sense. We didn't have as, you had warmer near close, and it's funny, or not funny, but interesting how Florence kind of took that path there, and then you still have a little pocket of warmth in there. It's kind of interesting how that works. And then, it did kind of modify a little bit, so definitely in the MDR region did warm up, and it did look a little bit more favorable a little bit later in the season. And currently, a little bit more warm than cold. I mean, there's definitely, some cold there, but there's definitely more warm. This definitely has more of a, slightly warm AMO, and we'll see how it progresses as we move through the season. This leads into the ACE index, and I'm sure most of you have heard this. If you read seasonal forecasts, you definitely have read this and heard about it. This is the Accumulated Cyclone Energy Index, okay? When you enter an SST setup like we have now, cold PDO, warm AMO, some interesting things start to happen, and we've kind of already touched on this. Remember, in weather, the atmosphere always wants to reach a balance. That's the goal, right? In 2010, the European hurricane forecast understood this balance trying to be reached by the atmosphere. I thought this was a very interesting forecast. They called for 23 named storms. Now, we only had 19, but they were on the right track. But what was really interesting is that the ACE index forecast, what was interesting in their forecast was really the ACE, not really the named storms. When you looked at it, they called for an ACE to rise to 125% globally, all right? So above normal globally. However, only 70% of normal across the entire Pacific Basin. All right, so at this point, we were definitely in a cold PDO. We had a cold Pacific. We had a La Nina going. There was a net energy deficit there, right? But what's interesting is they went 125% globally, 70% in the Pacific. But look at that in the Atlantic, 260% of normal in the Atlantic. So they understood this. It's not overly, complex when you really think about it. If the Pacific's cold and 2/3 of your tropical cyclone activity occurs there, you're going to make it up somewhere, right? And they saw that, and I thought that was really interesting, okay? So this makes perfect sense because when you have a huge area of water, which is the Pacific, that typically accounts for the large majority, 2/3 of tropical cyclone activity or energy, you lose this activity and energy because of factors like the cold PDO La Nina. And where do you think this atmosphere is going to make up for this? The Atlantic Basin, all right? So a lot of times it's not overly complex. If the Pacific's really cold, obviously it's just one piece, but it's an important piece. You probably are going to look to the Atlantic to have a bigger season. That's typically what happens in these situations. Not always, but typically. Okay. The phase total seasonal activity refers to the collective intensity duration of Atlantic named storms and hurricanes occurring during a given season. All right, so we're focusing on the ACE here. The measure of the total seasonal activity used by NOAA is called the accumulated cyclone energy, ACE. The ACE is a wind energy index defined by the sum of the squares of the maximum sustained surface wind speeds in knots, okay, measured every 6 hours for named systems while they're at least tropical storm strength, all right? So it's measured every 6 hours in these advisories when they get to tropical storm. We're not talking subtropical storms or depressions. However, this does not include the size of the storm, and that's important in my opinion, all right? So the ACE and PDI, Power Dissipation Index, both use calculations that take into account maximum wind speeds and duration of the storm. However, neither include the side of the storm. All right. So to me, that's a flaw with this. It's good because it's consistent and they've been doing it for a while, but I don't think it gives you the full picture because it's not looking at the size. I think that's important. Right. The third way is integrated kinetic energy, which does include the size, which in my opinion is better. All right. So how much energy is released by the hurricane versus how vast an area that will be impacted by the hurricanes. All right. So what is a great example of that? Katrina, Hurricane Ike. All right. Look at Katrina versus Camille. Camille was a more compact, powerful storm, but it didn't have the same amount of kinetic energy as Katrina. Katrina had far more kinetic energy, and this energy was distributed over a larger area that affected a larger area. Okay, so if you have two Cat 3 storms and one is 100 miles wide and the other one is 400 miles wide, are they the same? No, the 400 mile wide one's going to cause much more destruction. It has much more energy. All right, so that's a little bit of a flaw with this, in my opinion, and that's why I do think this integrated kinetic energy is better. All right, in my opinion. But NOAA uses the ACE index, all right, so we're going to focus on that. It combines the number of named storms, hurricanes, and major hurricanes to categorize the North Atlantic seasons as being above normal, near normal, or below normal. All right, don't memorize these numbers. Just put them out there so you have them. When you get above 111, that's considered above normal. When you are below 66, that's a total. That's considered a below normal season. When you're in that 66 to 111 range, you're in a near normal season, okay? The following tables I'm going to show you are from 1981 to 2010, and they look at the seasonal means and ranges for named storms, hurricanes, and major hurricanes during above normal, near normal, and below normal years. All the Atlantic hurricane seasons are looked at in this time frame, and this table highlights the marked differences in activity between the three seasonal types, okay? So it's a little bit of overgeneralization. Again, it's not considering the size, but it's directly related to the energy that the Atlantic is outputting, basically, all right? So when you get in these above normal seasons, and really when you get to 17 named storms, they call it hyperactive, that's when you get that above normal, and you see where they have the names of tropical storms. Don't memorize any of this. Again, I'm just showing it to you so you have it. I wouldn't make you memorize that. Definitely wouldn't put that on a final exam or a midterm. Obviously, this would be on the midterm, but I wouldn't just come up with some random thing like that, all right? It's just there for you to have. A season with an 8 index of 155 and above It's considered hyperactive. What I do want you to remember is 17 named storms is really considered hyperactive. Now, it does depend on the ace. You know, you can have a hyperactive season that doesn't quite have 17 named storms. I'll explain that in more detail. But in general, 17 named storms, hyperactive. Okay? Kinetic energy is proportional to square velocity, and by adding together the energy per some interval of time, the accumulated energy is found. As the duration of the storm increases, more values are summed, and the ACE also increases such that a longer duration storm may accumulate a larger ACE than more powerful storms or lesser duration. So this really comes down to how long is the storm going, right? If you have a Cape Verde storm that goes all the way across the Atlantic versus Katrina that forms close to the United States, the one that's going across the Atlantic is going to rack up a lot more ACE points, okay? Although ACE is a value proportional to energy of the system, it is not a direct calculation of energy. The mass of the moved air and therefore the size of the storm would show up in real energy calculations. Broadly speaking, the ACE is a measure of the power of the hurricane multiplied by the length of time it exists. So storms that last a long time as well as a particularly strong hurricane have high ACE values. ACE is calculated for only full advisories and tropical systems reaching or exceeding winds of at least 39 miles per hour, a tropical storm. And again, I talked about this. It does not include tropical depressions or subtropical storms. Okay. In 2017, Hurricane Irma generated 64.9 ACE units. This is the most ACE units generated by a single storm since Hurricane Ivan in 2004, which generated 70.4 ACE units. During the season, the ACE is based on operational advisories. And you need to keep in mind that the NAC will re-examine the data and produce a final report on each storm, which can lead to the ACE for the storm being revised upward or downward. All right. So until the final reports are issued, the ACE are still provisional. You'll see numbers during the season, but it's really after the season that they fine-tune this. All right. So let's look at some top ACE Atlantic years. Okay. 1933, we talked about that. Remember how I talked about it's likely they had more tropical cyclones? Why? Well, we didn't have satellites, so it's probably had more, which means this number is probably even higher. Which really, when you look at energy, now I know we're not looking at the size of the storm, and that is a flaw, but using a standard comparison, 1933 had more energy than 2005, and that's without those storms being counted. Interesting. 26, 230. You see some of these. Look at these big years recently. 95, 04, 17, 5. But what's interesting, look at this year here, 11. Now, first off, it could have been more because we didn't have satellites. But why was this 230 and this one with 28 storms was only 250? Well, even though you had less hurricanes, you had almost the same amount of major hurricanes, and you had more long-track systems. These systems were going across the MDR and the open Atlantic and racking up those ACE points more. There was actually more energy available, right? So what I've found too that I've noticed at least is sometimes when you have so much energy and you only have a certain amount of energy, right? And you have 28 storms. Well, obviously that year was bad, but there's only a certain amount of energy available. So if you have 28 storms, it's distributed over those 28 storms. But if you have the same amount of energy and you only have 11 storms, then that storm is probably going to be more powerful, at least for a longer period of time. Not necessarily at landfall, but there's more energy available for that system to track across the open Atlantic, all right? And look at the Pacific. You saw 92, 295 ACE units. Something kind of interesting, a side story with that. One of my mentors, Jim Leonard, the hurricane pioneer, the first guy that ever chased hurricanes. I've talked about him. He ironically, that year, no one did this at the time, he went to Guam in 1992 and chased a lot of these super typhoons, and he had an amazing year, and no one ever did that at the time, all right? So he went out there and saw all these storms. I mean, look at this, highest ACE year, right? But even though it was a weak year as far as names and numbers in 1992, what happened in 1992? Hurricane Andrew. And where is he from? South Florida. He lost his home in that hurricane. And what's crazy is, I know it sounds weird, he was really upset that he wasn't there for that, even though he had an amazing season in the Pacific. So just kind of a random side story, but kind of crazy that you go to the Pacific, you do something no one's ever done before, you get in all these super typhoons. The Atlantic Basin has a weak year, but it only takes one, and that one was Andrew. Some famous hurricanes, You got Hugo, Andrew. You might, sometimes people look at this like, wait a minute. Charlie only had 10. Katrina only had 20. Remember, these formed closer to the United States, okay, where Ivan tracked across the entire Atlantic basin, right? And it was a powerful hurricane, okay? So the duration is key, all right? And look at this, look at Harvey versus Irma. Harvey spun up real quick in the Western Gulf. Irma, came across the Atlantic basin. All right, so this leads into this next tip. We're actually heard from Joe Bastardi, and apparently his father was one of the people that discovered this. I guess his father was a meteorologist like him. And, from what I understand, he's one of the first to see the linkage between upward motion in the tropics and troughs digging further south. So as the land cools, you increase surface high pressure. We've talked about that. We're talking about the high pressure in New England and Canada. That's a normal thing to happen as the season goes on, especially you get in September and October and the land is cooling. You increase the surface high pressure. But in these big seasons, in these hyperactive seasons, it's not like all the energy in the Gulf and the Caribbean just goes away. It's not like, oh, it's December, energy, go away. It doesn't work that way. So you still have a lot of leftover rising motion, surface low pressure in the tropics. And how's air going to move high to low, right? So we're talking about hyperactive megayears, 19 named storms, or a high ACE, okay? So I would include 26 in this. Even though 26 didn't have 17 named storms, you had a hyperactive season according to the ACE index, all right? So the ACE plays into this as well. 17 named storms is usually hyperactive and a safe measure, but a high ACE also plays into this as well. So years such as 1933, 95, 69, and even 2005, you see the named storms, had notoriously cold periods before the new year, on the order of 30 to 45 days or longer. 1926 and 1950 is in the mix too. Technically, they didn't have 17 named storms, but the ACE represented hyperactive years. After either high numbers of high intensity years in the Atlantic Basin, right? So what makes this statistic even more interesting to me is these seasons are occurring independently from large-scaling signaling. So I'm going to show you here that it doesn't seem to matter whether it's El Nino or La Nina. If you have a hyperactive season and you have all this rising motion left over in the Gulf and Caribbean, troughs are going to come down and find that rising motion. So there was a La Nina in 1950 and 95, but there was an El Nino in 69, and neutral to warm, maybe not quite El Nino, but neutral to warm in 2005. So all different signals, right? So it would appear the only common denominator was the hurricane activity. This only increases the idea of the colder start to the winter season. All right, so let's talk about this a little bit more. All right, so again, 17 named storms, hyperactive, all right? But all these years here are still hyperactive, even if you don't have 17 named storms, because you have a high ACE, right? 1926 is a great example. Well, what's interesting is, these years, you did have an early start in the winter. Now, I know winter doesn't really start till what? December 22nd, right? Right around there. December 21st, 22nd. But the meteorological winter really starts December 1st. And really, in all extensive purposes, to me, about middle of November is really when winter starts to come, okay? On cold years, all right? So the faded December temps, and really the late part of November as well, may lie with the hurricane season. So if you have a lot of hurricanes, a mega season with 17 named storms or a high ACE, it means there's a heck of a lot of upward motion in the Atlantic Basin. Assuming there's still some hangover from the pattern that caused it, most likely there will. If you have a lot of upward motion in the Atlantic Basin, cold air is available to come quick. Where do you think this cold air is going to go? It's going to go towards where? That rising motion in the Gulf of Mexico and the Caribbean, all right? So why does that matter? Well, if you didn't have that rising motion, yeah, you get troughs digging in, but they're not going to dig in as far, okay? And they're probably not going to be as pronounced. Now, there's other factors involved in this, but it's interesting how these things are coming together. And I'll show you some more data behind this, all right? It's astounding the relationship between big hurricane seasons and the following December. 1995, big hurricane season, cold December in the east. 2007 was a slow dead season, and you had a warm December in the east. 2005, same as 95. Even in an El Nino year of 1969, you still had a cold December in the east. It has to do with the link between strong upward motion that produces enhanced tropical convection in the summer season and the leftover part of the pattern being southeast of North America for the front part of the winter. The large-scale movement of sinking air masses, cold, moves towards those air masses where there's upward motion or warmth. All right. So the land is cooling. It's getting really cold in Canada. You're building up that high pressure. You still have a lot of leftover rising motion in the Caribbean, Southeast Atlantic, Gulf of Mexico. That that cold air is going to want to rush towards that imbalance with that warm rising motion, high to low, and those troughs digging further south, and they lock in earlier on into the winter. The theory is the bigger indicator at the front part of the season, about November 15th to January 15th. Once the push of cold gets going and it wipes out the upward motion centers left behind by the warm waters near the coast, the pattern naturally goes back to a more normal pattern. So what do I mean by that? So when you're in this setup, this hyperactive setup, and you have this rising motion, these troughs are digging further south, and you get off to a quicker start to the winter, and the troughs are locked in, and it's colder earlier, eventually as these troughs keep working their way down, what are they going to do? They're going to start to destroy that upward motion, right? The cold air and that dry air is going to come in through the tropics, and it's going to start to negate that upward motion. So after about 45 days or so of that, it's going to wash out. That upward motion is going to go away, and now you're going to return to more of a, when I say normal pattern, other drivers are now going to start really leading to what's going to happen in the winter. So it's going to be more of a factor with the SOI, which is El Nino or La Nina, NAO, AO, things like that, which we'll talk a lot more about when we get to long-range forecasting. All right. So again, what's cool about this is it seems to be independent from these other large-scale indexes. So if you have this rising motion, you have this hyperactive season, typically, at least from my research and from what others have researched, it looks like we're going to have a cold start of the winter. It works really well. So let's simply look at two mega seasons, 1995 and 2005. We'll look from Chicago to New York City. In 1995, December was a combined 3 degrees below normal, a little bit above 3, or a little bit colder than 3 degrees below normal, where January and February was only 0.5 degrees below normal. All right, so it was going to be probably a below normal season regardless, but that upward motion really pronounced in the early part of the winter. Pretty interesting. Look at 2005. December was 3 degrees below normal, but January and February was +6 above normal. I found that pretty interesting. All right. Again, there's probably other things involved. There's no way to say that this is end all, be all, and it works perfectly. But you got to admit this is interesting, and it's something I've noticed, and it works really well. It's probably not going to work always, but it's definitely a solid tip. So last thing we'll end on here, we know when we're in phases 8, 1, and 2, what does that mean? And also into 3, but really 8, 1, and 2, rising motion in the Gulf, Caribbean, right? And that leads to what? More tropical development, 4 times more likely. But we've been using MGO more and more now to forecast temperatures, right? So let's look at this. This is a temperature composite of December, January, and February. And we're looking at phase 8, 1, and 2 here. And look at that. Cold in the east, pretty cold in the east, still pretty cold in the east. So what is that saying to me? Well, 812 usually have rising motion in here, and troughs like to move towards that rising motion, all right? And that's how they're starting to use MGO now for temperature forecasting, because where this rising motion is going to help you know the pattern. And then pattern recognition is key, especially in long-range temperature forecasting. If you know where the troughs and ridges are, you have a much better chance of forecasting the temperatures. If you can't even get the troughs and ridges right, you're not going to get the temperatures right. Okay. All right, I know that's a little bit more complex. Like I said, as we move on to each lecture, the levels it's going to go up a little bit more and more and more. It's up to you to use the ones you like. But I really like that last one. That hyperactive into an early winter season works pretty well. Is it always going to work? No, because nothing in weather always works. But you're playing the odds, and it definitely seems like the odds are in your favor. So when I see a hyperactive season, I'm going to be forecasting a cold winter, at least at the beginning part, and like that November 15th to January 15th time frame. All right, so that's it with part 3 and lecture 4, and I'll be back shortly with lecture 5.